everyone to this new episode of the Water Underground Talks. Today is my great pleasure to welcome Professor Sebnem Arlsan from Ankara University. Welcome, Sebnem.
Thank you, Viviana. I'm very glad that I am here now with you.
Great. So let's start the first part of the video with our interview. So the first question that I would like to ask you is how did you first develop a passion for water?
I really wish that my answer to this question would be I always, when I was a little kid, I was always interested in groundwater, but this is not a reality. Actually, I always had a passion for teaching. And after studying geology for 2 years, I was starting to think that this discipline is not right for me, and I was not very much interested in the geology part. But when I got my first hydrogeology course in the third year, I thought that this discipline is really the right one for me because it had a lot of mathematics, physics, and I was always interested in the that part. And I also had an amazing journey with the chemistry as well. So after I got my first hydrogeology course, I started thinking about groundwater, actually, how precious it is and how invisible it is to us, actually. Maybe because we don't get enough education in our high school years about hydrogeology. So we are all unaware of the um, importance of this resource. So this is how it all got started.
Oh, great. So the second question we have for you is how does your personality or your personal interest make you a better scientist? You probably anticipated something with the previous answer, but we really want to know more about that.
Well, I when I think of myself, I actually define my personality as being persistent. I'm strong-minded, so I never give up. I always try to get better, and whenever I am unsuccessful, I really do not want to lose time feeling sorry for myself. Instead, I really want to try new ways to be successful. So I think that those my personality makes me good scientist.
Yes, indeed. I think we all have to deal with failures, and taking the bright side to as a way to improve, I think, is really important. So we should all learn from your very positive attitude. So thank you for sharing. And talking about your work and something that we are going to see more in details in the second part of the talk, um, what do you think is the impact of your work or your research out of academia? So what are the perception or the feeling that you have in this regard?
I really thought about mm, this question. This is a really hard one for me because for the time being, I really think that my work outside of the academia, the impact is a little bit low. But I wish that it will have a huge impact in the future, especially in science policy making. So I not only my work but also my colleagues' works should be considered when the policymakers are making laws and making decisions about our precious resources. They should also have a look at our publications, but for the time being, I only would like to, after the pandemic, would like to visit, for example, high schools and tell high school students about the groundwater resources, the
Yeah,
importance.
it's very important. And also your work in providing high quality data that we will see about in a bit is really, really important. So I think you stressed a very good point in highlighting the importance of having good data to be transferred to policymakers. So I'm sure you will succeed. So now we're going to move to the second part of our talk, and I'm very excited to know more about your work, and in particular to be guided by you in this amazing journey, in particular to see more on tracing the exciting underground journey of the water molecules with isotopes. So please.
Thank you so much. Thank you so much for giving me the opportunity. I'm very excited. Today, I would like to talk about the exciting underground journey of water molecules with isotopes, as Viviana said. So I am sure you all know where our Earth's water is. It's actually trapped inside the groundwater aquifers, 30% of the freshwater resources, but unfortunately, most of it is actually in the oceans. 96.5% of it, and the Earth is a really watery place. 71% of it's covered with waters, but the freshwater resources that we have are limited, and as we can see from this picture, groundwater resources are our biggest supply. So we have to investigate them not only by using the conventional methods, but also by using the new, rather new ones. So environmental isotopes, actually there are two types of isotopes, the artificial ones and the natural ones, which are called environmental isotopes, that have been used in hydrogeological studies a lot during the last maybe 60 years. So there are stable isotopes and radioactive isotopes. Stable isotopes are actually used to understand the source of a groundwater molecule, the recharge processes, and their variations are governed by isotope fractionation. So if you think about the water cycle, the huge, enormous cycle of water in our Earth, we consider the beginning of this cycle as the ocean, since this is the biggest reservoir of water in the Earth, and we don't know where it ends. It doesn't end. It's always continuing. So this is a complex cycle, actually. All of the processes happening there is very complex, but the isotopes, oxygen 18 and deuterium, the stable isotopes of water, has got rather predictable properties inside this water cycle. So and the variations of the these isotopes are defined by Craig in 1961, and we call this as the global meteoric water line. So there are a lot of elements present in hydrogeological systems, and they all have isotopes, but we as hydrogeologists are only interested in a few of them. What could be the reasons? Like we are interested in the isotopes of carbon, hydrogen, oxygen, sulfur, but not the other elements. I want you to think about this, and this is my first research question for you. So the radioactive isotopes are actually used primarily to measure age or residence time. So we have different radioactive isotopes, and their half-lives are different. For example, tritium has got a half-life a little bit more than 12 years, but carbon-14 has got a half-life of more than 5,000 years. So we can choose which isotope to use by firstly investigating the groundwater system that we are going to work in. So while working with environmental isotopes to solve a groundwater problem, we are very much interested in the isotopic composition of rain. Can you think of the reasons? So if we don't have a rainwater sample, we can always find a seasonal spring that we can use instead of a rain sample. The reason actually behind this is hidden inside this water cycle. One molecule starts its journey in the atmosphere by evaporating from the oceans. It travels and then it might fall to the surface in a mountainous region, and then it might infiltrate and reach to the water table, and it will become a groundwater molecule. So can you think of other hydrogeological problems besides groundwater origin and mixing that stable isotopes can help us solve? So this is my second research question for you. And another one is about to come. If I take a sample from a deep confined aquifer, how would its isotopic signature be different from a rainwater sample that we collect from the same site today? These are, I hope they are not very hard. These are, I want to leave for you. So if we talk about the radioactive isotopes, I would like to tell you the difference between groundwater age and groundwater residence time concepts, which are explained in detail in a book that I am citing here. So the groundwater residence time is actually so it starts with the recharge of a groundwater molecule, and it ends with the discharge. So it is a natural process, and the discharge can happen as a discharge of groundwater to a surface water body, or discharge of groundwater as a spring, but it should happen in a natural way. So if we talk about the groundwater age, then we can say that the time elapsed between recharge and pumping, for example, pumping of a water sample, the time elapsed between recharge and pumping would be considered as groundwater recharge. So as you can see, we have got some isotopes like krypton 85, tritium, carbon 14. We have got some others that we use in hydrogeology, and as I told you before, they all have different half-lives, and they all have different limitations. For example, tritium has reached its natural background levels. It was once very high in the atmosphere due to the nuclear testing happening mostly in the northern hemisphere. And one complication, for example, is that the decay starts actually in the unsaturated zone, and we are always interested in the processes happening in the saturated zone. This is one complication of the radioactive isotopes. Another complication is that we always have mixing. So mixing of different water parcels having different residence times. Actually, when we sample a well, we always have mixing of waters with different ages. So is it really possible to know the exact age of a water sample? If you ask me this question, I will say that it is actually impossible. But can you think, do we really need to know the exact age, or the apparent age, or can we proceed by knowing only the age of a mixture? So I really would like you to think about this. When we talk about groundwater, we actually do not use the word mining. I really like this word. So if we talk about the age of a groundwater sample, then we can talk about groundwater mining. It's very usual to talk about gold mining. So gold is very precious, as we all know, and it is very expensive. But what about a groundwater resource? If we are mining, if we are taking the water out from a deep confined aquifer, which was only recharged thousands of years ago, what are we doing? So when we talk about the year of recharge, why it is very important to know about the timing of recharge. So if we are talking about days or years, there is we can say that there is modern recharge to an aquifer. So what happens if there is modern recharge? Then we always think about contamination issues, for example. So modern groundwaters are always susceptible to contamination. But if we have recharge in climatic conditions different from today's, we should always talk about sustainable management of the groundwater resources. Then we should ask ourselves, are we mining groundwater? Are we mining a renewable source or a non-renewable source? So there is a article published recently in Nature Geoscience, which is about the global aquifers, and they say, the authors say that the aquifers are dominated by fossil groundwaters, but they are also vulnerable to modern contamination. I was very much amazed to find out about this publication, actually. In this article, fossil groundwaters were defined as groundwater recharged by precipitation more than 12,000 years ago. So I used to think that if there was recharge 12,000 years ago, then there won't be any modern contamination. But actually, the authors find out that half of the wells that they examined have dominated by fossil groundwater, and they also contain detectable levels of tritium. So tritium normally is used to give us information about modern recharge. So the authors actually suggest us that we should also consider the water quality risks along with sustainability when using groundwater resources. I hope you also would have a look at this paper. So about my favorite papers, well, actually, cooling of tropical Brazil during the last glacial maximum paper, which was published in Science in 1995, is one of my favorite ones, because when I first read about this paper, I was very much amazed to find out that groundwaters are actually used to construct paleoclimates temperatures. So paleo temperatures like noble gas temperatures help us to find out about the air temperatures. I was very much amazed, and I couldn't actually imagine myself being the first author of an article, of a similar article published 18 years later. And this actually publication received a reward, an award, 2013 Coolest Paper Awards from the Early Career Hydrogeologists Network. So after receiving this award, I went to Marrakesh and met Viviana there. And also I met Professor Chen, which also who is also working about the paleo groundwater resources. So he invited me to Tallinn and Dublin, and also to China, and it all seems like my travels were, I was in a dream. So now we are unable to travel, and we have to stay home for our health. But I am sure that we will start traveling again, and we will get through this pandemic. And I really hope that I will meet you in some place, maybe in an IAH conference. And I would like to thank all of my professors and everyone who actually made me made me a good scientist today. And I would also like to thank Water Underground Talks for giving me this pleasure and this opportunity to talk about my research. Thank you so much for listening.
So thank you very much, Sebnem, for guiding us in this amazing journey in the underground. And I agree with you. I really hope we can all meet in person soon. And I hope some students that are watching the video will come and tell you the answer for the question, the very interesting question that you raised in your talk. So once again, thank you for being with us with the Water Underground Talks. Thank you.
Thank you so much for inviting me.